What's up, everybody? I'm Harpreet Sahota. I'm joined here with Jacob Marks. He's a research scientist at Foxhole 51. And we're joined by Yu Yang, who will discuss their paper, A Textbook Remedy for Domain Shifts, Knowledge Priors for Medical Image Analysis, which was accepted into NeurIPS 2024. This paper is really interesting because it's a vital challenge for medical image analysis, the vulnerability of deep learning to what's called domain shifts. As you know, deep learning has been a huge breakthrough for image recognition in a lot of fields. Its application to medical images has really not seen that same kind of progress, and that's due to a fundamental problem. Models trained on one data set often fail dramatically when they're presented with images from different sources, patient populations, or even different scanning equipment. For example, if you were to build a system that's trained to diagnose pneumonia from chest x-rays that were taken at one hospital, if you take the same model and you deploy it at another hospital using different imaging protocols, the system's accuracy will plummet. And this, of course, will harm patient care and patient outcomes. And this inconsistency stems from domain shifts, which are discrepancies between the data used for training and the data that's encountered in the real world. Yu's research offers a compelling solution called Knowledge Enhanced Bottlenecks, or KnoBo. And KnoBo draws inspiration from how medical professionals learn by first mastering foundational knowledge from textbooks and then applying that knowledge to interpret patient cases. And this research demonstrates that KnoBo really enhances model robustness to domain shifts, and it ends up outperforming conventional deep learning approaches on various medical image data sets. Not only that, but the interpretability of KnoBo models promises to increase trust among clinicians and help facilitate broader adoption of AI in healthcare. Yu, thank you so much for joining us, and I'm excited to jump into your paper. Go ahead and take it away.
Great, thank you for the introduction. I'm Yue from UPenn, and I will introduce our paper, A Textbook Remedy for Domain Shifts, Knowledge Priors for Medical Image Analysis. This is a joint work with Penn Engineering and Penn Medicine. Last few decades, we've seen great success in deep models in general domains. But for critical domains like healthcare, we found it's still very challenging to deploy those deep models in real world. So what are the problems? We identify two issues here. The first is the data. It is very hard to scale data in medical domain because of the privacy or safety issues. And also those data are biased, are skewed over some demographic variables. Another issue is the architectures we designed for general domain may not be appropriate for medical domains. So for the first issue, the data, we found the distribution of those demographic variables are uneven in medical data. So for example, on the left side is the distribution of race in the Czech expert dataset. You can see most of the data are from white people and few of them are Black and other races. And on the right side is the skin lesion datasets. You found most of the patients are light colored and few of them have darker skin. So those can be very problematic because a lot of research found those deep models are very good at identify those demographic variables from the image. They are better than human expert in identify those demographic variables, and they are very sensitive. So to deploy such models in real world, we need more robust models. But is the existing deep models robust enough? So we can test their robustness in these domain shift experiments. So basically, we can construct the dataset in a confounded way. So we can find some confounded factors like sex here. So we can confound the positive cases to a confounded factor like female and confound the negative cases to male. And we switch this confounding combination in the testing data. So we can construct in-domain and out-of-domain for test. So we can do the same thing using other confounding factors like age, young people and old people. We can use race like Black people or white people. And those black box models, they can do pretty well on in-domain data, but they are just mainly taking the shortcut using those confounding factors as spurious correlations to make the diagnose. And when testing them on the auto domain, when the confounding factors just changed, they can drop significantly. So these are very serious problems. And why this is happening, we identify another issue for the deep models architectures. So there's a well-known feature for the deep models, and they have very good priors for general domain, like images of cats or dogs. And the deep image prior means those models, even without any training data, randomly initialized, they can still be a very effective feature extractor for those natural images. And we can verify this by doing such experiment. We can have our baseline just directly using the pixel values from the images as feature. We just resize the image and flatten them into features and pass them through a linear layer for some classification task. And to compare with this baseline, we can grab some very popular vision backbones like CNN or VIT. And to be noticed, those models are untrained, randomly initialized. And we use those untrained models to extract features, also pass them through linear layer, and we can compare their accurate prediction accuracy. And we noticed on natural images, like images from ImageNet, those deep vision backbones like CNN or VIT, they are more effective than pixels. They can outperform pixels. They have better deep image priors, which allows them to generalize real on auto domain data. However, for medical images like X-ray or skin lesions, we found those deep image models, they perform worse than pixels. Especially for X-rays, we can see pixel has better accuracy than the CNN or VIT, which means those models do not have a good priors for medical images. And this is a serious problem because without a good guidance from the priors, model can only rely on the data to learn its parameters. And if the data is biased, has some uneven distribution over some demographic variables, it can just taking shortcuts using those confounding factors, and it will cause them to have catastrophic failures on auto domain distribution. Okay, how can we overcome this challenge? In our work, we mainly inspired by how medical students are trained. So there are two phases for training a medical student. In the first stage, the students are sent to medical school to spend a few years to learn knowledge from textbooks. And then they are sent to hospitals for residency to practice on some real cases. Existing deep models, they kind of skip the first stage. They directly train the model on the data. In this case, they may not rely on the knowledge in textbooks when making diagnose. And our KnoBo will just incorporate the first stage, just trying to get knowledge priors from textbooks into the system. Our main idea is we want to ground those medical diagnoses onto some knowledge. And how to get the knowledge? We are getting knowledge from medical documents. And for the model architecture, we are using this architecture called concept bottleneck models. You can refer to those two papers for some background about this model. The main idea is very simple. Compared to end deep black box models, this concept bottleneck model will first predict on some interpretable concepts. For example, here, the concepts here are some knowledge that doctors will use when reading the X-rays, like is there a collapse of lung? Is there any ground glass opacity? So we get some intermediate predictions on those interpretable concepts. And then using the interpretable intermediate predictions through a linear layer to make your final label prediction. In this case here, we predict this is a COVID patient. And to build such model, we need to first find the structure prior, which is how to construct this concept structure. And then second, how to do the bottleneck predictor, how to ground the images onto those concepts. And then finally, we need to constrain the model using a parameter prior we invented. So for the first step, constructing the structure prior, which is find the concepts, we use the retrieval augmented generation. We use a query like how to diagnose COVID from X-rays, and we retrieve from medical corpus. Here we choose different types of corpus. For example, for PubMed, which is the largest corpus for medical articles, we have 5 million articles. We use the query to retrieve relevant documents about COVID. and we find some relevant documents and pass it through large language model to summarize the concepts, which is like a binary questions here. And then we can keep using the concepts we find through the retrieval system to find more relevant documents to iteratively construct the concept bottleneck. So this system has a few advantages. Those concepts we generated are attributable. You can find which document can support this knowledge. And we can then further ask human experts to do some fact check to double check whether this knowledge is valid or not. After getting the concepts, we need to ground them onto the images. For example, given one image, we want to know yes or no given these concepts. And we leverage a pre-training dataset which contains X-rays and a paired clinical report. And we annotate data using large language model, like given this report, is that true or false for ground glass opacity, this knowledge? And we can annotate the data using language model. So for example, here, we want to learn a binary classifiers for each concepts. And we have a lot of clinical report. We let language model to split them into positive and negative reports. And then we train on the associated X-ray images to train a binary classifier for each knowledge. And then the last step is we want to constrain the model learning using parameter prior. We want the parameters to align with some human decisions. Because the linear layer is a weight matrix, and this matrix has some semantics. The dimension is the number of concepts NC by the number of classes. So each element of this matrix will denote the affinity score between a class and a concept. For example, here this node denotes the correlation between COVID and ground glass opacity. And given the domain knowledge, we know those two terms are positively correlated. So we can predefine this element as positive one. Another example here, like for the disease cardiomegaly and the concept normal heart size, we know cardiomegaly means abnormal heart. So we can assign -1 to indicate those two terms are negatively correlated. So using this predefined weight matrix, during learning, we want the learned linear layer to be aligned with this predefined weight matrix. And we just simply using a L1 distance to minimize their distance. So here is an overview of our KnoBo system. Given the input image, we learn structure priors, which is a concepts generation system to get the knowledge that will be useful to diagnose X-ray images. And then we're using some pre-training multimodal data with clinical report to train a grounding function for each of the concept. And then using the concept bottleneck predictor, we can get the predictions over those concepts and then pass them through a linear layer, which will further be constrained by the parameter prior. And for the evaluations, we constructed a lot of confounded datasets using different confounding factors. We also evaluate on 2 different modalities, chest X-ray and skin lesion. For each modality, we construct 5 different confounded datasets. And here are the main results. We compare with end-to-end training, which is a black box model weight. We just fine-tune the weight on those datasets. You can see the blue dot here is auto-domain performance, and the triangle is the in-domain performance. VIT can get very high performance on in-domain, but mainly you leverage the confounded factors as a shortcut. And it will have very poor performance on auto domain, which has achieved a better balance between in-domain and auto domain. And it improved over the auto domain by a large margin and achieve a much higher performance on average. Here are the overall performance on 2 modalities. We can see KnoBo improve over weight by 6% on X-ray and 59% on skin lesion. And we also did some abolition study on the knowledge resource, like which kind of medical corpus is better for building this structure prior. And we found PubMed is a quite promising resource, which gives us higher accuracy and more diverse concepts. And the diversity here is just using some sentence similarity to measure the differences between the concepts generated from different resources. To conclude, in this work, we show medical documents can be a very reliable resources to build medical knowledge. And we also found using interpretive models with knowledge priors from those medical documents, we can construct a more robust model in domain shifts. So that's it.
You, thank you very much for the presentation. Really appreciate you giving us an overview of your paper. I'll turn it over to Jacob first and see if Jacob has any questions. Then I'll go over to my questions.
I'll say the same thing as Harpreet. Awesome work. This is incredible. My parents and sister are doctors. So the thing that you were talking about where you have to learn from textbooks first and then you actually do the practice is, and they always say like, you see one, then you do one, then you teach one. It's kind of like the MO in medicine. So love the motivation here and the results, I think, speak for themselves. One question that came up throughout this is the process that you go through in order to find related concepts and then to kind of build out that corpus of related knowledge. Then the fact that you're training classifiers on each of the concepts in a binary fashion along the way. Each of those steps seems like it's not too time intensive, but when you add it all together, I could imagine that it takes a while to generate some prediction at the end of the day. Could you speak to the time cost of all of this?
Yeah, so actually they are quite efficient because we only generate the bottleneck once. We just run it for one time to get all the concepts. And also the bottleneck predictor for each concept also run once. Like we just like train classifiers for each concept and it can be reused in the future. I think that's a tentative solution for now because we are lack of good foundation models for medical domains. If you have a very powerful multimodal models for medical, we can skip a lot of those steps. We don't need to train a classifier for each concept. We can just using something like a foundation model to directly give you some score between an image and a concept. But for now, unfortunately, there's no such powerful medical foundation models. We do try a lot of foundation models existing. They are not performing very well. So we need to train a classifier for each of them. We want to build specific classifiers for each knowledge, rather than rely on a very good foundation model. So I
Yeah,
think it's a solution for now. Yeah.
that makes sense. That makes
Mm.
sense. And then in the plots and results page that you showed, where you had the comparison of in-domain and out-of-domain performance, and it's remarkable just how much better KnoBo is able to perform than Vision Transformer. But there is still that slight gap, and I guess that depends. The size of the gap differs from task or domain to domain. What do you think could close that gap? Do you think that the quality of the corpus that you're using, like if PubMed were to get even better, would that help close it? Or would you need some additional idea or part of the pipeline to generate that and close the gap?
Yeah, we still notice those deep end-to-end models still have advantages for in-domain performance because they can leverage all the informations from the images to make the prediction. But our models, because we constrain the model, only rely on knowledge to make the predictions. So it kind of has some information loss. We definitely will have some gap with those black box models. But I think there are several ways to narrow the gap, like build a more comprehensive knowledge bottleneck that will cover more cases, that will help you to avoid losing a lot of information. That's one part. Another part is having a better feature representations for the medical images, because we found still we don't have a very good medical image feature extractor, and even we train our own medical clip model, is still not perform as we expected. So in the future, maybe more powerful foundation models for medical come out, we can get better features and which will improve the intermediate prediction accuracy of those concept predictors, and then we'll give you better downstream performance. Yeah.
Awesome. Awesome. Thank you so much. I think that's all the questions that I have.
So I've got a question about this concept of deep image priors. And the paper kind of suggests that these are weak or even harmful for the existing visual backbones for medical images. I'm wondering, if you could maybe explain this concept of a deep image prior in more detail, and perhaps maybe elaborate on why some of these existing architectures might lack effective priors for medical data, and how does KnoBo's integration of the medical knowledge try to address this issue?
Yeah, great question. The deep image prior actually is a kind of very old terms. It first identified in like 2011, like over 10 years ago. In short word, like those deep image prior, the prior is some data agnostic assumptions about the task you're going to solve. Even without looking at any data, you may already have some assumptions about how I can tackle this task. So this is the definition of prior. And people found for like CN or VIT, the architecture, like how they do the filtering, how they identify the edges or the textures from images, they are very good assumptions about how we should read the images. Some other people may call the prior called inductive bias. And those things are very useful for domain generalization because you are not only rely on one domain to train your model, because you have some domain invariant assumptions about the task. This will help you to generalize to some other domains. So this inductive bias of those models or deep priors of those models facilitate the success models on like ImageNet or some other data sets. Those are very important feature about deep models. But medical images, although they are like 2D array, looks like images, but they are totally different modality. So some of the architecture designs we build for natural images may not be applicable for medical images. We may not have good priors for medical images. And like, because like for doctors, they read images rely on some background knowledge. Their priors are from textbook, not purely from X-ray only, right? So we need something else. We not only need like the X-ray data, we need something else from textbook, from medical documents. So that's our intuition to why we need to find more priors from medical documents. Yeah, I think that's my answer. Yeah.
Okay. Yeah, there was an acknowledgement of the paper that there needs to be a reliance on kind of these large labeled medical data sets for KnoBo. But the data sets like that are quite scarce, especially for like the rare conditions. I'm wondering how you envision KnoBo kind of being adapted or applied in those type of situations.
Yeah, that's challenge for medical fields that some rare disease has fewer data. It's hard to collect more data for them. And I think medical domain may need a different paradigm. Maybe the scale up the data is not the only way, because for humans, they are not reading tons of X-rays to be an expert. And I think we may rely more on other modalities, like we can rely more on the language side, because like for we have a lot of language data for medical. How can we leverage those knowledge in textual side to guide us to do some multimodal tasks to understand medical images? That could be a very interesting direction in the future. And we do have some ongoing projects trying to leveraging the articles from PubMed and just only using this publicly available data to try to build a multimodal model. And we may need more objectives, not only like next token prediction or some generation objectives. We may have some other objectives trying to like do some imagination or do some like some other predictions using the text data from PubMed to build a better foundation model for medical.
Speaking of, other modalities, we talked about, using medical textbooks and articles as a source of knowledge, but how do you see KnoBo evolving with, new forms of medical knowledge? For example, like, we have patient generated data through like wearables, like for example, Apple Watch or Fitbit or like the Aura Ring, or even large scale genomic kind of data. How do you envision kind of these modalities working into KnoBo?
Yeah, I think because in real cases, doctors make diagnose not only rely on one modality. It will ask questions about patients, rely on some other statistics like blood test or some other test. All those informations will give you a more comprehensive judgment about the patient. So I think unite different types of modality, leveraging diverse types of information will definitely give you a more robust medical model. And there are some ongoing progress in general domain, trying to unify like video data, audio data, all types of data. I think those techniques may be transferred to medical domain, trying to unify different modality, different types of information, and then give you a better or more robust medical agent. Yeah.
I've got one more question lined up, but before I get to that, seeing if Jacob might have another question that he'd like to ask. If not, I'll go ahead and jump into mine.
Go for it, Harpreet.
Awesome. So, quite curious here about, you talk about the potential for KnoBo to improve interpretability. I'm wondering how could this interpretability kind of lead to more newer applications of deep learning AI in medical education? For example, providing more personalized feedback to medical students, or maybe even helping them and assisting them in understanding some really complex medical concepts in school or even cases that they come across in the field.
Yeah, that's a great question. And one big advantage for interpretable models is it provides an interface for human to interact with the models. So human can understand why model makes such prediction by looking at those interpret predictions. So that's a great idea that we can use those models to teach junior doctors to learn from senior doctors, like how we should like diagnose such a disease. And I think that could be a very interesting direction in the future. Like, how can we use this as an educational tool to teach junior students? And another advantage for interpretable model is it allows human to intervene the model. Like, if you find the model rely on some wrong concepts when making some predictions, you can modify the concept, you can edit concepts, you can add more concepts, you can change the model architectures to make it perform better or more robust in some tasks.
Thank you so much for joining us. I'm looking forward to meeting you at NeurIPS. Please come by the Voxel 51 booth at NeurIPS. We'll hook you up with some swag, some special swag for speakers like you, and look forward to meeting you there. And again, thank you so much for taking time to join us today.
Yeah,
Cheers.
thank you. Thank you. See you then.
Thanks so much.